And there is a structure. I mean, there is a structure, and we know there is a structure because we look at them in time, and this is a y-t plot. This is time. This is different from the wall. And you are seeing here something which is the intensity of the Reynolds stress at any given point, okay? And then you see that there is some things which are the ejections which are going up, some things which are the sweeps which are going down, okay? And what else, okay? Well, people have been looking at these Reynolds stresses for a long time. I mean, from the very beginning, people knew, of course, the energy equation had been known for a century, okay? And then they realized that the mechanisms were the Reynolds stresses and tried to understand the Reynolds stresses. And the first people who did that were Loan Wilmers and Jim Wallace in the 1970s. And basically what they did is, okay, well, let's do a joint PDF of the string wave velocity fluctuation and the span wave velocity, and the normal velocity fluctuation. The product of these two things are the Reynolds stresses. And this joint PDF looks like an ellipse. And you want to see the places where these Reynolds stresses are large. And that means things which are outside this hyperbola in there. And then you see that those things are mostly in this quadrant or in these quadrants, okay? And these structures are called quadrants because of that. And what happens here is that the string wave velocity is negative and the wall normal velocity is positive. So these are flow coming up and bringing low velocity fluid up, okay? This is the ejection. And here what you see are the sweeps in which the string wave velocity is positive because the velocity is coming down, okay? And it's creating a high velocity fluid in there, okay? So these are the sweeps and the ejections, okay? And then, of course, this was 1970s, 40 years later, or 30 years later, okay? We know everything about that. I mean, ask the questions, I can answer the question. And we know how the ejections look like. They look like this, okay? They look like more or less conical structures, okay? And conical structures, these are these green things, okay? In which the flow is going up. Side by side, there is a sweep, okay? There is the ejection is here, the sweep is there. So in between, there is something like a roller, like a large-scale vortex, okay? And the large-scale vortex is a way of understanding this. And the structures, sorry, the streaks have also changed. They changed from something like this, that was what happened in the 1970s, to something like this, which is what happens now. I mean, they are still long, but they are now much bigger, and we see what they do. And they're connected. We have the ejection to one side, the sweep to the other. When the flow is coming up, you get a low velocity streak. When the flow is coming down, you have a high velocity streak, and blah blah blah. Okay. We also know that things are multi-scale. I mean, I told you that the things are multi-scale. Well, they are multi-scale. These things happen at all scales. I mean, when they are short, they are not very tall. When they are longer, they are much taller. This is the length. This is the height. And this is a joint PDF of the two things. They look like this. This is basically the basic model of that, and we understand that more or less. We told you that this is burst. Okay, we can also measure that now. I mean, this is something that can be measured. That, I mean, all of this is basically, I don't know what you want to call it, artificial intelligence. It's persistence. I mean, we know what we are looking for, and we teach the computer how to look for it, and the computer finds it, okay? And then this is the history of one single structure. And these actually are complicated things because in the meantime, this thing has broken into pieces and they reconnected. We are following the main branch, if you want. And these things have a lifetime, and the lifetime is also proportional to the length. So everything is similar, and we know they're going up and going down. I mean, we know all these things, okay? So what are we learning about that? Well, remember, what we wanted was a model. And up to now, we didn't have a model. But right now, we saw this. I mean, these things is something that grows, reaches a maximum, decays, okay? Well, there was a theory for that, and it's a very old theory for that. It was done by this guy, Orr, in 1906, okay? Orr was a meteorologist, and he realized that you don't need to be unstable to grow. The problem is that if you are not unstable and you grow, eventually you will decay. Okay? But that's okay. I mean, you're growing. I mean, you're creating a structure. Okay? And basically, what the mechanism for that is you have a structure, one normal velocity structure that is leaning backwards, and then the shear moves it forward. Okay? When you are vertical, then the one normal velocity is very happy because it can go up and down. So the one normal velocity is maximum. And then you keep moving forward, you lean forward, and the one normal velocity becomes unhappy because now you cannot go up and down. Okay? So you decay again. So this is something this is the theory. So we tested this in a minimal channel. Remember, the minimal channel is this toy problem in which we can look at time without worrying about spatial chaos. And the same thing happened. I mean, this thing here is the inclination of the structures, okay? And this is the intensity of the structure, and you see the structures going like this, growing, decaying, like this. And then this thing was repeated not for a minimal channel, but for a full channel by my student, by Miguel Encinar, okay? And the same thing happened. So this is nice. I mean, this is nice because now we have a theory, and we have a theory that we can test, because now we can go to the flow, look for a burst, okay, and see where do you think coming from, and that we can do that because we have a history. So we do a conditional average of what is the flow before this burst and what is going to happen later, and you see when you look before, you get something that is weaker, is smaller. Like look at this gray thing, and it's tilting backwards. I mean, you can see the bump is there. This bump keeps moving forward, and at the end you tilt forward and die. Okay, and in the meantime, something else has happened. I mean, you die, but you have left your children in there. The streaks have been created. Okay, you see there is no gray streak there. This thing is getting bigger and bigger and bigger and bigger. Okay. So this is a nice model, okay? So we have a theory. Fantastic. I mean, remember, this is what made people happy with free shear flows. They have a theory, okay? So now we can start to think about control or things like that, because we understand what is going on. You have bursts, and the burst grows because of the shear, and this is the OR mechanism. The burst creates the streaks, and then decays, the burst decays, but the streak is left there, so this is kinetic energy being put into turbulence, and then the streak becomes unstable and creates a new burst. We have a theory, and it looks like a nice theory. First it was obtained by the collaboration of the researcher. He's a big guy here. And the postdoc, this computer postdoc that did all the work for us, is look at the million pictures of a million structures and did the statistics and blah, 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 blah. It looks like a nice theory because, you see, when you look at these things here, they take something like 8% of the volume, but they represent 60% of the drag. So that looks like, okay, we have done something, okay? But remember, you have to be skeptical. What happens here, okay? How does this thing happen, okay? Just by chance, things become unstable, and they happen to create a new vortex. Why don't they create a new vortex in another place that is a wrong place? So this is the first question that is left open, okay? What exactly closes this cycle, okay? We don't know that. I mean, we really don't understand that yet. And until we understand that, we cannot be happy, okay? There's other things which shouldn't make us happy, okay? The first thing is, remember the streaks, okay? These are the streaks, okay? To scale, this is a burst. The burst is short, the streak is long, okay? How? I told you the vortex creates the streak. But how can a short thing create a long thing, okay? I just don't know. I mean, I'm telling you, open problem. This is a second open problem, okay? What exactly closes the turbulent cycle? What makes a short burst into a long streak? There are other problems which are left, and I'm not going to put all of them here, but there's another one which is, to me, is something that you really makes me unhappy. What happens to all these multi-scale things? I mean, how do these structures talk to each other? And they have to talk to each other because they carry the Reynolds stress, and the Reynolds stress has to be constant from the wall to the top. This is the momentum flux. The momentum cannot disappear in the middle of the channel. So they have to. This small structure here, which is near the wall, has to know that has to have the same intensity as this large-scale structure out there. How do they talk to each other? They have different lifetimes. I mean, this guy is much shorter lived than that guy. Okay, so it's like me trying to discuss with a blue whale what do I do with the sea. I mean, we have different scales. I mean, we just cannot. We don't talk about the same thing. There is no reason why these things are talking in there, but we still have a model. Okay, we still have a model. Which makes us happy, and with a few open questions. And the next thing I want to do is, okay, I want to convince you that, well, the open questions are secondary questions. Okay, do you agree with that? Who doesn't? I mean, who agrees with that? We have a basic model. I mean, we have the turbulent cycle, and we have these minor things in there that have to do with interaction. I don't agree with that. I mean, actually, at that point, I wanted to finish this talk and even put the thank you there, and then realize that, thank you for what, okay? First, I mean, there is this question. I mean, there are things that I don't understand that makes me unhappy. And then there is another problem, which probably, I mean, many of you are asking yourself about, okay? This is a course about data. I've been talking to you about physics. Why I haven't been talking about physics and telling you, okay, we do this with somehow. I mean, we have 100 terabytes, and I mean, doing things with 100 terabytes is always going to be a problem, but we do it, okay? Well, I want to defend myself, okay? First, I want to erase that thank you, okay? Well, I want to postpone it a little. And then I want to tell you a tale. I want to tell you a fable. The fable of the planet Mars, okay? Something that I showed these things sometime. So, I mean, some of you might have seen it before, but I think this is an interesting tale, okay? This was Mars when I was a child, okay? This was the best picture that you could get of Mars through the best telescope on Earth. And you see, these are the northern highlands. These are the southern lowlands. Okay, and we recognize it, but then people didn't know anything about lowlands and highlands. They knew this, okay, and they knew it changed with seasons. Then they made theory for that, and it was the best theory that people could make at the time. Remember this: observe, explain. Okay, this is the scientific cycle going on. Observe, explain. Okay, and the explanations were completely wild. I mean, I think about them now, and wow. I mean, how could these people do this? There were canals. There were at some point there were Martians. Okay, one of the first papers that I remember, the first scientific paper that I remember fishing out as a child, basically, because it came in the newspaper, and then I became excited and looked at it somehow. I don't know where I found it, but I found it. Okay, some guy had actually detected the footprint of the spectrum of chlorophyll in there. Okay, so well, these are plants. Okay, and this paper was in Science actually. So these things, I mean, the explanation went completely wild. Why? Because there were no data. They were working on this, basically on this and basically on that. I mean, there were no more data than that. Okay, this is Mars today. I mean, we have robots in there, and we know that Mars doesn't look like there doesn't seem to be canals. Certainly no chlorophyll at any amount that can be detected from Earth. It looks like New Mexico or like Algeria or something like that. Okay, this is the next part of the cycle. This is the test. Okay. And what happens? Well, this thing fails. Okay, this thing is not true. Okay, this is the scientific method working. Okay, basically, what the data does for you is not to tell you what things are. It doesn't tell you the truth. It tells you what is not the truth. I mean, this is the only thing that the data tells you, okay? They can tell you, well, this is not true. If you want to know what is true, you have to keep going through the cycle and blah, 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 okay? For everything else, to understand things, to be able to move forward to the next problem, you need a model. And what I have been trying to tell you through all this hour is that, okay, data is very important, data analysis is very important, but you need a model. You cannot forget the model. Keep going through the model. Don't forget that. And then now I can say thank you.